From the periodic table, carbon is known to have the electron configuration 1s2, 2s2, 2px1, 2py1, which will not provide 4 equivalent bonds to carbon in a molecule like methane shown here. In organic chemistry, we find it useful to convert the linear representation of the electron configuration into an energy diagram. Here we can clearly see that 1s is lowest in energy, 2s is next, then 2p are the highest. 2s and 2p are the valence orbitals. We could use the valence orbitals here to pair up with other atoms and form bonds. However, those bonds would not be identical like they are in methane. We need to come up with a better model for how these orbitals are used. What if we take one of the 2s electrons and promote it up to the 2p level? This gives us 4 unpaired electrons for bonding, but they are not equivalent in energy yet. Instead, we can mix the s and p orbitals, which is 4 in total, and come up with 4 so-called hybrid orbitals that are equivalent in shape and energy, with their average energy being somewhere between s and p. These are sp3. Since we are still looking at carbon, we have 4 valence electrons that will fill up these equivalent sp3 orbitals singly. This gives us 4 unpaired electrons of equal energy that are housed in orbitals of the same shape and size. Since these sp3 orbitals are the same shape and size and they each contain 1 electron, they will repel equally. This generates a tetrahedral shape for the atomic and then the molecular orbitals. Extending this idea to nitrogen and ammonia with only single bonds, we need to add an extra electron to the sp3 model for carbon. This will explain the distorted tetrahedral shape as well as the nitrogen lone pair. Now when we occupy the valence orbitals, we must add the extra electron for N, which results in the valence sp3 orbitals filling singly, before we have to double up the extra electron. That gives 3 single electrons for bonds and a non-bonding lone pair. Similarly, for oxygen and water, we will use sp3 atomic orbitals, since there are no pi bonds present, and explain the lone pairs and eventually the distorted tetrahedral or bent shape of the molecule. We need to add an extra electron compared to N, which will double up to give the second lone pair. The orbital picture is the same as it was for C and N, however we must add the extra electron from oxygen. This gives us 2 equivalent lone pairs, as required in the water molecule, as well as 2 unpaired electrons that go towards sigma bonds. When we move to alkenes, which contain a pi bond as well as sigma bonds, we must change the hybridization pattern to match the need for p orbital overlap to give the second component of the trigonal planar double bond. Since we need a pi bond, which is formed by overlap of adjacent p orbitals, we need to leave a p orbital alone and only hybridize the s and 2 of the p orbitals. This gives us 3 times sp2 orbitals and 1 p left over. Placing electrons in orbitals begins with filling the sp2 hybrid orbitals singly. Then we realize that doubling up the 4th electron is going to take more energy than placing it in a slightly higher energy p orbital. We now have a pattern that will contribute to 3 sigma bonds and 1 pi bond. Putting 2 sp2 hybrid carbons next to each other, we are able to make 3 sigma bonds to other atoms. The remaining p orbitals may then be parallel and able to overlap to give the pi bond. When nitrogen is involved in 1 pi bond, we use the same sp2 model. However, we must add the extra electron compared to carbon, which will double up to give the lone pair. Again, we need a p orbital left over for the pi bond. The sp2 picture is essentially the same as for carbon, however we have an extra electron to deal with. We add single electrons to each sp2 orbital, then the 4th to the p orbital. We now have to go back and double up in one of the half-filled sp2 orbitals. When oxygen is involved in 1 pi bond, it also uses the sp2 model. We have to add 1 more electron, and then account for 2 lone pairs of equal energy, and the need for 1 sigma bond and 1 pi bond to the adjacent atom. Occupying the orbitals in sp2 oxygen begins with the hybrid orbitals and then the slightly higher p orbital. The 5th and 6th electrons then must double up in the lower energy hybrid orbitals. This gives us 2 lone pairs, a single electron for a sigma bond and a single electron for a pi bond. The last pattern we study is when the central atom is involved in 2 pi bonds. We have a third model, sp, that will account for carbon being able to form 2 sigma and 2 pi bonds when it's found in molecules like alkynes. For sp atomic orbitals, we only mix 2 of the available orbitals, the 2s and 1 of the 2p. We need to leave 2 of the p orbitals unchanged in order to accommodate the 2 pi bonds. This gives us 2 same energy hybrids and 2 same energy p orbitals. When we place the available 4 valence electrons in these orbitals, we again add to the lower energy hybrids first. It takes less energy to then add to the slightly higher p orbitals, rather than double up. This gives us a pattern that will contribute to 2 sigma bonds and 2 pi bonds. When we put 2 sp hybrid carbons next to each other, we can complete the molecule by overlapping the hybrids to form sigma bonds, which will be 180 degrees apart in a linear arrangement. The orthogonal p orbitals also overlap, above and below the sigma framework, to form the 2 required pi bonds. Nitrogen is also able to form 2 pi bonds, so sp hybridization is needed here again. We must remember that N brings an extra electron when compared to carbon. The sp picture is essentially the same for N as it was for C, so we have 2 sp orbitals and 2 untouched p orbitals. There are 5 valence electrons from N to distribute, with the first 2 going into hybrids and the second 2 going to p orbitals. The 5th electron will double up in a hybrid orbital. This is the lone pair, with the unpaired sp electron going to the sigma bond and the 2 unpaired p electrons going to the 2 pi bonds. While C and N form triple bonds readily, and therefore need the sp model for 2p orbitals, this is not the case with oxygen, since both hybrid orbitals would be occupied with lone pairs. Overall, when we consider what hybridization patterns are needed for each situation, if only sigma bonds are involved, we are using the sp3 model. If 1 pi bond is present, we use the sp2 model, and if 2 pi bonds are involved, we use sp. Lone pairs will always go in hybridized orbitals for C, N, and O.